Distance learning curricula in machine learning, evaluation of machine learning models. Good afternoon and welcome to the machine learning course. This course was developed as a result of the Erasmus Plus project Code-In. All you need to learn is internet access and a computer. The course contains a total of 10 topics, and in this topic, we will say something more about the evaluation of machine learning models. Evaluation plays a critical role in machine learning, as it allows us to assess the performance and reliability of models. It helps answer essential questions such as, how well does the model perform? Is it accurate and reliable? Can it generalize to unseen data? Proper evaluation provides insights into the strengths and weaknesses of the model, guiding us in making informed decisions and improvements. Without evaluation, we might unthinkingly trust inaccurate or poorly performing models, leading to wrong predictions, flawed decision-making, and potential negative consequences. Furthermore, evaluation enables us to compare different models and select the most suitable one for a specific task, enhancing the overall quality of machine learning applications. By evaluating models on diverse data sets, we can gain confidence in their ability to perform well in real-world scenarios, thereby increasing their practical utility. Evaluation is an ongoing process, as models may require periodic re-evaluation and refinement to adapt to evolving data and changing requirements. It ensures the model meets the desired objectives and requirements, leading to reliable and effective results. Evaluation metrics are the secret sauce that helps us measure and understand how well our classification models are performing. Think of evaluation metrics as a performance report card for our models, providing valuable insights into their strengths and weaknesses. Today, we will explore some of the most commonly used evaluation metrics that are our trusty guides for building accurate and reliable models. Common evaluations include the following: accuracy, precision, recall, F1 score. Understanding these evaluation metrics is essential for evaluating the effectiveness and reliability of machine learning models. Considering these metrics, we can make informed decisions, fine-tune our models, and optimize their performance. The confusion matrix is a valuable tool that aids you in evaluating your classification model. It acts as a guiding compass, providing insights into your model's performance. Understanding the matrix and associated metrics are like accuracy, precision, recall, and F1 score is crucial for assessing your model's effectiveness in classification tasks. Visualize a grid representing your model's journey through a vast data landscape. One side of the matrix holds the true classes, the actual presence or absence of the target, while the other contains the predicted classes, the labels your model assigns. Every step your model takes is recorded within this matrix. During your exploration of this intricate landscape, various outcomes are possible. Your model may correctly identify instances, true positives, misclassify some instances, false negatives, accurately classify negatives, true negatives, or incorrectly label negatives as positives, false positives. These outcomes determine the contents of each cell within the confusion matrix, providing valuable information for evaluation purposes. With the confusion matrix and its associated metrics at your disposal, you can now embark on an exciting journey of evaluating your prediction model. By analyzing accuracy, precision, recall, and F1 score, you can assess the model's effectiveness in predicting the presence or absence of diabetes. So let's dive into these metrics and discover their power in evaluating your classification model. Accuracy measures how well our model predicts positive and negative outcomes. It is calculated by dividing the number of correct predictions, true positives and true negatives, by the total number of predictions. In this case, we have a total of 9 correct predictions. 6 is true positive and 3 is true negative. The model's accuracy is calculated by dividing the number of correct predictions, which is 9, by the total number of predictions, which is 12, resulting in an accuracy of 0.75 or 75%. Precision focuses on the accuracy of positive predictions made by the model. It is calculated by dividing the number of true positive predictions by the sum of true positives and false positives. Precision helps us understand how well the model performs when it predicts an item as positive. The precision of the model is determined by dividing the number of true positive predictions, which is 6, by the sum of true positives and false positives, which is 6 plus 1, resulting in a precision of 85.7%. Recall measures how well the model correctly identifies the positive outcomes. When considering the recall of the model, we divide the number of true positive predictions, which is 6, by the sum of true positives and false negatives, which is 6 plus 2, resulting in a recall of 0.75. That means that the model successfully identified 75% of the apples. The F1 score is a balanced measure that combines both precision and recall. It provides a single value representing the model's overall performance by considering false positives and negatives. F1 score is calculated using the harmonic mean of precision and recall. After performing the calculation, we obtain an F1 score of 0.8003 in this model, indicating a balanced performance of the model in capturing both precision and recall. By understanding these evaluation metrics, you can assess your models in different aspects, such as overall correctness, precision, recall, and the ability to rank instances. This knowledge helps you make informed decisions, refine your models, and optimize their performance to achieve better results. Use mean squared error as a mistake calculator that measures how well your predictions match the actual values. It takes the difference between each prediction and the actual value, squares them to eliminate negatives, adds them all up, and then divides them by the number of predictions. The smaller the mean squared error, the fewer mistakes your model is making. So the goal is to keep mean squared error as low as possible. Imagine R squared as your model's popularity score. It tells you how much of credit your model deserves for predicting the target variable. R squared ranges from 0 to 1, where 1 means your model is a superstar. If your model gets an R squared of 0.8, it explains 80% of the variability in the target variable. The higher the R squared, the better your model captures the patterns and trends in the data. Mean absolute error is like a size-agnostic critic, focusing on your mistake's average size. It takes the absolute difference between each prediction and the actual value, adds them all up, and then divides by the number of predictions. Unlike mean squared error, mean absolute error doesn't care about squaring the differences, so it's not sensitive to extreme outliers. The lower the mean absolute error, the closer your predictions are to average values. So in summary, when evaluating your regression model, you use mean squared error to see how close your predicted measurements are to the real measurements, R squared to measure how well your recipe explains the variations, and mean absolute error to determine the average difference between predicted and real measurements. These metrics help you fine-tune your recipe and ensure you're baking the most accurate positive model. Among the evaluation metrics for clustering, the silhouette score and Davis-Baldwin index are the most important metrics. They provide complementary insights into the quality of clustering results. The silhouette score assesses the separation and compactness of clusters, while the Davis-Baldwin index considers both the within-cluster scatter and between-cluster separation. Considering these two metrics together can provide a more comprehensive understanding of the clustering performance and guide the selection of the optimal clustering solution. The silhouette score ranges from -1 to 1, with -1 representing poor clustering quality, 0 indicating overlapping clusters or data points on cluster boundaries, and 1 indicating well-separated and distinct clusters. Imagine you're at a party where people are grouped into clusters based on their interests. The silhouette score measures how well defined each person's cluster is, like how comfortable they are within their own group compared to neighboring groups. For example, Alice's silhouette score is 0.622. Alice's silhouette score of 0.622 indicates that she is reasonably well matched to her cluster and is more similar to members of her cluster than the nearest neighboring cluster. Think of the Davis-Baldwin Index as a scorecard for a fun clustering game. It helps us determine how well data points form clusters based on their similarities. We calculate the average distance to their cluster center for each cluster. Then we measure the distance between different cluster centers, showing how separate the clusters are. We get a single number by plugging these values into the DBI formula. The lower the number, the better the clustering. Picture two clusters competing in a thrilling dance competition. Cluster 1 showcases their moves with an average distance of 1.43, while Cluster 2 dazzles the audience with an average distance of 2.03. The distance between their center stages is 2.04. We crunch the number using the DBI formula and arrive at a score of 0.848. That indicates a remarkable balance between the clusters, suggesting a high-quality dance battle where each group brings its unique style to the floor. In conclusion, evaluating machine learning models is essential to assess their performance and determine their suitability for real-world applications. To complete this unit, study and review the following online resources. Thank you for attention.